In this video, we are going to discuss about a design technique known as backtracking. Backtracking is used to solve large instances of difficult combinatorial problems. Backtracking is a more intelligent variation. The principal idea here is to construct solutions one component at a time and evaluate such partially constructed candidates as follows. If a partially constructed solution can be developed further without violating the problem's constraint, then it is done by taking the first remaining legitimate option for the next component. If there is no legitimate option for the next component, no alternatives for any remaining component need to be considered. In that case, the algorithm backtracks to replace the last component of a partially constructed solution with its next option. It is convenient to implement this kind of processing by constructing a tree of choices being made, and it is also called as the state space tree. Its root represents an initial state before the search for a solution begins. The nodes of the first level in the tree represent the choices made for the first component of a solution. The nodes of the second level represent the choices for second component and so on. If a node in a state space tree is said to be promising, a node in a state space tree is said to be promising if it corresponds to a partially constructed solution that may still lead to a complete solution. Otherwise, if the selected component does not lead us to a solution, then we call it to be a non-promising node. Leaves represent either non-promising dead ends or complete solutions found by the algorithm. So whenever you encounter a non-promising dead end, then you backtrack to its previous node. In the majority of cases, the state space tree for backtracking algorithms is constructed in the manner of depth first search. If the current node is promising, its child is generated by adding the first remaining legitimate option for the next component of a solution, and the processing moves to its child. If the current node turns out to be a non-promising node, then the algorithm backtracks to the node's parent to consider the next possible option for its last component. If there is no such option, it backtracks one more level up the tree and so on. Finally, if the algorithm reaches a complete solution to the problem, it either stops or continues searching for other possible solutions. So now we shall look into the application of backtracking. A problem known as n coins is a good example of the application of backtracking. The problem is here to place n queens on an n cross n chessboard so that no two queens attack each other. So when do we say that two coins attach each other? If We say so if the following conditions are met. That is, two queens attack each other by being in same row or in the same column, or if they are on the same diagonal. For example, if n is equal to 1, then the problem has a trivial solution, and it is easy to see that there is no solution for n is equal to 2 and n is equal to 3. So therefore, let us consider a 4 queens problem and solve it by making use of backtracking technique. Since each of the 4 queens has to be placed in its own row, all we need to do is assign a column for each queen on the board represented in this figure. We start with an empty board and then place queen 1 in the first possible position of its row, which is row 1 column 1. That is, we try to place the first queen in column 1 of row 1. We start with an empty board and then place queen 1 in the first possible position of its row, which is column 1 of row 1. Then we try to place queen 2 after trying unsuccessfully column 1 and column 2 in the first acceptable position, for which it is square 2 comma 3. So once I place queen 1 in the first column, first row, I cannot place the second queen either on the first row or on the first column, because as the constraint specifies, if I place the queen on either of the first row and the first column, or if I place the second queen diagonally, then queen 1 may attack queen 2. So therefore, the possible second solution for placing the second queen is to put the second queen on the square 2 comma 3, that is second row, third column. So if you notice here, the queen 1 is not going to attack queen 2 either horizontally or vertically, neither diagonally. So now, once I place queen 2, I cannot place queen 3 either on column 3 or on row 2, nor can I place it diagonally. So once I place queen 2 on 2 comma 3, I cannot place the third queen on column 3, nor can I place the queen 3 on row 2, nor can I place the third queen diagonally on this chessboard. So therefore, I have no solution to place or no place to locate queen 3 on this chessboard. So therefore, I backtrack to queen 2. So therefore, when I backtrack to queen 2, the next possibility for us is to place queen 2 in the next possible solution, that is at row 2 column 4. So when we place queen 2 on row 2 column 4, it means that we cannot place queen 3 either on fourth column, second row, and we cannot place queen 3 in the diagonal position. So similarly, when queen 1 is occupying the first column, first row, queen 3 cannot be placed either on row 1 nor on column 1, and similarly cannot be placed on the diagonal. So therefore, if you observe, if you observe, we are left out with row 3 column 2 to be the right place to put queen 3. Right? Row 3 column 2 is the right place to put the queen 3. But now once we place queen 3 onto this row 3 column 2, it means that we cannot further place queen 4 on this row 3 nor on any cell of column 2, nor can we place queen 4 diagonally, right? And as queen 2 is at this location, you cannot place queen 4 on column 4, nor can it be placed on any cell of row 2, and cannot be placed diagonally too. And similarly, as queen 1 is on the first row, first column, we cannot place queen 4 on the first row, nor on the first column, and nor on any of the cells in the diagonal. So it means that you have no position to place the last queen, that is queen 4. So what we do is we backtrack to queen 3. So we backtrack to queen 3. We have already observed that queen 3 doesn't have any other proper position except from the cell 3, 2. So therefore we backtrack to queen 2, and we have observed that queen 2 is already in the second row's last column. So she has no other position to relocate. So therefore we now backtrack to queen 1. So queen 1 was initially placed on the first row, first column. So now queen 1 shall slightly be relocated to the position first row, second column. So once we put queen 1 on the first row, second column, then we cannot place queen 2 either on first row or on second column, nor can we place her on the diagonal. So as queen 1 may attack. So therefore, the next proper position for placing the second queen is at the location second row, fourth column. So once we place queen 2 in this position, the next choice for placing queen 3. So when I place queen 2 at the location second row, fourth column, it means that queen 3 cannot be placed on the second row, nor can she be placed on the fourth column. And as queen 1 is already onto the first row, queen 3 cannot be placed on the first row, nor queen 3 can be placed on the second column, nor she can be placed diagonally, and nor she can be placed diagonally with respect to queen 2. So therefore, only possible location for queen 3 to be placed would be at the cell 3, 1. So when I place queen 3 at the location 3, 1, I cannot place queen 4. I cannot place So we cannot place queen 4 on the first column, third row. Similarly, as queen 1 is on the second column of the first row, you cannot make use of the entire second column nor the first row. And similarly, as queen 2 is at the location 2, 4, you cannot make use of the fourth column and the second row, and you cannot make use of the diagonals. So queen 3 is here, so you cannot make use of this diagonal. Queen 2 is here, so you cannot make use of this diagonal. So therefore, only position that is left out for queen 4 is the cell. That is the cell 4, 3. So we have placed all 4 queens such that they are not attacking each other. So all these nodes that show a cross say that they are the non-promising nodes and we do not get solutions from it. So therefore we try to eliminate them.